This is lecture 14 of Condensed Matter Physics 1. And we are today going to start with discussion of crystal structure. So, let us first understand what it entails. So, let me start with determined structure of sodium chloride. This has been done experimentally and we will be learning how it is done. So, what it has is this cubic arrangement of atoms. It's a little complicated, so let me try making it. So, here is the chlorine atom, and then you have, let me make this one the sodium atom, and then you have chlorine on the sides, and then on both sides, and then you have alternatively sodium again, then chlorine here, chlorine here, chlorine here, and sodium, sodium, then on the corners I am making all sodium atoms, and in between there are these chlorine atoms. I may have missed one or two somewhere, but this is how it is, right. So, there could be others. There will be one chlorine right in the middle, then there will be one sodium here, and so on. So, what it is a regular arrangements of atoms which could be of one kind or different kinds. An example which has become popular lately and is easier to visualize is that of graphene, which is a two-dimensional structure, and in this the underlying pattern is like this. It's what is known as honeycomb structure. So on, and these carbon atoms are sitting at these corners. Again, a regular arrangement of atoms, so which is repeated, and we need to find a system or develop a system to describe this regular arrangement. So, our job right now is going to be to develop a system to describe this arrangement. Once I do that, then I have a system through which I can define something in one unit which is repeating, and then I can describe the entire crystal. So, for this, let me first give you the definition of what are known as Bravai lattice. So, a lattice is a regular arrangement of points. Okay, and then I add the atoms to these points, then it becomes a crystal. Now, for example, in the case that we saw, I have this NaCl where these points are at the corners, they are here also, backside points I will make with red, and then there are these points all over. Similarly, in the graphene example, I have these points. So, let me remove the lines and show you that there is a regular arrangement of points. On the corners of a hexagon. This is the kind of arrangement one has. So, in this, this is a lattice, but is it a Bravai lattice? So, I am going to now define something called the Bravai lattice. This is going to be an S. If all the points on the lattice can be given by the relationship. So, let us say there is a point which has a vector r for point P. This is equal to some n1 a plus n2 b, all the points. Then this is known as Bravai lattice. An equivalent statement would be that in a Bravai lattice, the arrangement and orientation of lattice would look the same. From any point. And these vectors A and B, I am talking in the context of 2 dimensions, are known as primitive vectors. Now, if you generalize to 3D, so let me just repeat 2D Bravai lattice. I would have any point vector is equal to n1 a plus n2 b, and for 3D I would have this point r, any point for a point P would be n1 a plus n2 b plus n3 c, and a requirement is that n1, n2 and n3 are all integers. So let us look at the examples that we took. If I look at this 3D lattice on which I have points at the corners as well as at the center of the faces. No matter which point you go to, you have to need a little bit of imagination. Everything would look the same all throughout. So this, we'll find what the primitive vectors are, but this is a Bravais lattice, because we said if everything looks the same, then it is a Bravais lattice, and therefore I should be able to find those primitive vectors. On the other hand, if I look at this hexagonal lattice, let me make it first. Four would be enough to make the point, and here are these points. So if I look at point P and point Q, let me complete it on this side also, so that it is clear what we are talking about. You can immediately see that on point P, I have a point on the left and two on the 60 degrees. At point Q, the orientation is not the same. There is a point to the right and 2 points on the left. So, orientation of the lattice is not the same from points P and Q. Oh, sorry, this is not a vector. P and Q, and this implies honeycomb lattice is not a Bravais lattice. So, we need to find what the Bravais lattice corresponding to such a structure is. After all, it is a repeating pattern. So, in this particular case, in the graphene case, and I am doing it with a purpose, where I have these atoms sitting here and here. I can take a vector like this, call it A, take another vector like this, call it B, and then I generate different points. Now, in this case, you would notice that if I take the vector out here to be, say, V, V is not equal to N1 A plus N2 B with N1 and N2 as integers. So how do I describe this point, the red point out here? How do we describe this point, this atom? So in this case, what we do is, for each point we assign 2 carbon atoms. So the answer to this question is, for each lattice point, because the red atom site is not a lattice point, assign 2 atoms. So what I have is, I have a lattice point here, I have a lattice point here, I have a lattice point here, and then I can take the combinations and generate, and this will come out to be a lattice like this. I'll ask you to make it, and at each lattice point I give 2 atoms, one here and one right here, and then you will be able to generate this entire graphene structure. So this, what we call, is the basis. Why I did this is to motivate that when we assign a basis to a lattice point, this gives a crystal structure. Again in 2D, think of it like this. Suppose I have a set of tiles put on the floor. This certainly is a Bravais lattice of points. Where I have these lattice points right here, and this is very plain, bland structure. Now on each tile I have some pattern. So what I am doing is I am adding a basis to it. At each point, so I am taking a basis, lattice point, this is my Bravais lattice, and on this lattice I am at each point adding this pattern. Which is the basis. So in a crystal, 2-dimensional or 3-dimensional, this basis is formed by a collection of atoms or molecules. All right. So what we have learned through this is that a crystal structure can be described by a Bravais lattice which is formed by primitive vectors and this is coupled with a basis at each lattice point. So this is what we have learned through this. And why I am emphasizing again this primitive part is because we will see that sometimes it is more convenient to describe a lattice by some other means, although it does have these primitive vectors, it is a Bravais lattice, but you give it some other name where it becomes more convenient to visualize. Now, to understand it better, let us look at the Bravais lattices in (2D). Now, keep in mind that when I am talking about this, I am talking about orientational and translational invariance about each point. So, no matter which point I go to, the structure should look the same both in the orientation and arrangement. So, this also gives rise to some sort of a symmetry, which I will talk about in a few minutes. So, if I look at a set of points which are connected by, let us say, a vector A and vector B, magnitude of A need not be equal to magnitude of B, and the angle between them, let us call it phi. Phi is arbitrary. It could be 45 degrees, it could be 33 degrees for all you know. What it would create is starting from a point, another point, and it will keep creating these points. So, this forms a Bravais lattice, what is known as an oblique lattice. The arrangement also has some sort of a symmetry, and here the symmetry is if I rotate the whole thing by pi, which is equal to 2 pi by 2, it comes back to itself. So, it has a two-fold symmetry. Okay, so that is one kind of lattice. Next, I make it more symmetric, because these are repeating patterns, they have some sort of a symmetry. So, next I make what is known as the square lattice. In this case, I would have these points on the corners of a square, so that A and B are such that modulus of A is same as modulus of B, and the angle phi between them is 90 degrees, which is 2 pi by 4. So, I can rotate this whole thing by pi by 2, and the lattice comes back to itself. So, lattice can be rotated by 2 pi by 4 and comes back to itself. So, this has a four-fold symmetry. That is the other kind of lattice you can have. Generalizing this, I have rectangular lattice, which is pretty much like square, except that A and B are not equal. So, I have vector A, vector B, and their lengths are not equal, but the angle phi between them is 90 degrees. Now, here I cannot rotate by pi by 2 and come back to itself. So, this should be rotated by 2 pi by 2, that is pi, to come back to itself. So, this is a two-fold symmetry. So, I have given you three kinds of lattices. The two more that can be described in 2 dimensions. Next, I am going to say centered rectangular lattice, and what I have here is this rectangle and in addition there are these points in the middle. So, let me connect them. There is this rectangle and these points in the middle. Now, here you notice if I take this A and this B, A is not equal to B, the angle phi is 90 degrees, but the middle points cannot be connected to these points, the points at these corners of the rectangle, through A plus B with integers as their multiples. So, this is not a primitive cell, or A and B here are not primitive vectors. You can also see why not. The points in the at the center of rectangle cannot be obtained as N1A plus N2B. The primitive cell in this case is like this. Here is A and here is B. And now you can see that all the points can be now written as the vector for all the points can be written as N1 plus N1A plus N2B. So, A and B shown here are primitive vectors. So, what you have on the left hand side here is the conventional cell, and what you have here is the primitive cell. You also notice the difference. In conventional cell, there are two lattice points in a conventional cell of rectangular centered rectangular. Not all, but centered rectangular has 2 lattice points, whereas primitive cell has 1 lattice point. Again, in this case, A is not necessarily equal to B, and depending on what their magnitude is, the angle could be different. And a special case of this comes as hexagonal lattice, and in this lattice again you have A and B, and these are the lattice points. Let me make them a little bigger. These are the lattice points. And here is the angle. So, in this case, the length of A and B vectors are equal, and phi equals 120 degrees. And you can take the lattice onto itself by a rotation of pi by 3, which is 2 pi by 6. So, this has a 6-fold symmetry. These are the only Rabi lattice that you can have in 2D. A very famous example of what you cannot have is the 5-fold symmetry. In which case you would have points on the corners of a pentagon, and what you will see is that this symmetry is not consistent with translational symmetry. That means, if I add these pentagons together, I would not have the lattice coming back to itself with 5-fold, where I have to do a rotation of 2 pi by 5 to make these each cell to come back to itself, but then the entire lattice does not come back to itself. So, this does not make a crystal, and if you try to make it, what you will see is there are gaps in between which are not covered by these pentagons. So, this is not allowed. Similarly, 7-fold symmetry is not allowed. Now, we go to 3 dimensions. Again, I have all the lattice points given by n1 A plus n2 B plus n3 C, and the most general lattice you can have is where A mod A is not equal to mod B is not equal to mod C, and the angles are arbitrary. So, let us call angles alpha between B and C, beta between A and C, and gamma between A and B, and what you have is a lattice like this. So, here is the vector, and these vectors are not coplanar. So, here is vector A, here is vector B, and then you have a vector C. And then any combination. So, you would have a cell like this. And this will keep on repeating. What is known as a trigon lattice. Then you can add more and more symmetries and come up with many different lattice types. Overall, there are 14 lattice or Bravais lattice in 3D, and what I will do is upload the different types with this lecture. What I want to focus on right now is the most common ones, the most common lattices that we will encounter, and there are others, but in this course mostly we will be dealing with cubic, so all the points will be at the corners. Then I will have body centered cubic, where I have points at the corners, and one at the center of the body. So, let me show it by making these diagonals and showing that this is right where the diagonals cross. So, this is body centered cubic or BCC. And the third one that I have is face centered cubic, where I have these points at the corners, and in addition I have points at the center of each face. So, there are 6 of them and one on the back side. Just to show that they are at the center of this face, let me draw the diagonals on the face. So, here is one right here, then I have one on the top face right here, and so on. So, this is face centered cubic or FCC. Now, you can see in the cubic case, each point is shared among 8 of those. So, in this case I have exactly one lattice point per cell, and therefore, it is a primitive that the vectors here are primitive vectors. On the other hand, in BCC, if I take A along here, B in this plane and C going to the top and take this as the cell, there are two lattice points here, two lattice points per cell. So, it is not a primitive cell. Primitive cell will be something different. So, this is a conventional BCC cell, and here in the face center you have 1 plus each face point is shared between 2. So, there are 3 plus 1 4 lattice points per cell. So, this is also a conventional cell, and since this is a Bravais lattice, I should be able to find the primitive vectors corresponding to these. So, let us do that now. So, conventional BCC, I have one cube, then next cube, and let me make this one on the back side, and make one at the bottom, and suppose I take the point out here as the origin. Then I have lattice points right at the center of each of these cubes. And suppose I take this direction to be x, this direction to be y, and direction going to the top as z. Then the unit cell is made by primitive vectors A here, B here, and C here. And you can write A as, if the cell size is a cube of side A, each of this would be making angle 60 degrees from x, y, and z axis. So, I can write A as equal to A by 2. A is x unit vector plus y unit vector minus z unit vector. B, you can see from here, is A by 2 minus x plus y plus z, and C, again you can see, is going to be A by 2 x minus y plus z. These form the primitive vectors for the BCC, conventional BCC Bravais lattice. Now, the volume of a cell, this you know from vector calculus, is modulus of A dot B cross C. And you can calculate this here, and you will find this to be A cubed by 2. The conventional cell has volume equals A cubed. So, the primitive cell having a volume of A cubed by 2 makes perfect sense, because number of lattice points in conventional cell is 2. So, in A cube by 2 you are going to have exactly one lattice point, number of lattice points in primitive cell is going to be 1. So, I have shown that although in BCC it appears as if it may not be a Bravais lattice, but from the orientation from going to each point you know it is a Bravais lattice. So, I have been able to find D primitive vectors and form a primitive cell. Let us do this exercise for conventional FCC. In conventional FCC, this is the conventional cell. I have points at each corner, and then I have points on each face. So, the number of points in conventional cell is equal to 4 in a volume of A cubed. From the argument that I gave in connection with BCC, you know from here that primitive cell should have a volume of A cubed by 4. Let us define those vectors. So, I have this cell, this direction is x, this is y, this is z, and the primitive vectors are defined as A going to the face point here, middle of the face, B going to the middle of face on the back side, and C going to the middle of face here. So that vector A, the primitive vector, is equal to A by 2 x plus y. Primitive vector B is equal to A by 2 y plus z, and primitive vector C is equal to A by 2 x plus z, and the volume is going to be A dot B cross C, and you can check this comes out to be A cubed by 4. So, I have also defined the primitive cell or primitive vectors for FCC. So, with this introduction to Bravais lattice, let me conclude the lecture. We have shown that a crystal is lattice and to which we add a basis. We have defined what Bravais lattice are, and related to this are the primitive lattice vectors and primitive cell. And finally, we discussed cubic, body centered cubic, and face centered cubic lattices. Thank you.